Hello everyone, welcome back to our channel. So today we are studying noise pollution in a very easy, conceptual and exam oriented manner. This video is specifically designed for UGC NET JRF Environmental Sciences, GATE Environmental Sciences and Engineering, ICAR ASRB NET Environmental Sciences, UPSC and State PCS Environment Section and other relevant environmental sciences and engineering examinations. This video will cover noise pollution, its causes, effects, important formula, numericals, previous year questions and some MCQs and other relevant international and national noise standards which are very important in cracking such type of examinations relevant to environmental pollution and specifically noise pollution. So stay focused till end because this video will strengthen your conceptual understanding and numerical solving ability. Now before starting the topic, concepts and numericals, let me briefly introduce myself. So in this session, we will cover the complete topic of noise pollution numericals, including decibel concepts, SPL and SIL, sound level calculations, important numericals, measurement instruments, health effects, standards, control measures, and exam-oriented MCQs and some previous year questions. So let's get started. Now let us begin with the fundamentals of noise pollution. In this session, we'll mainly focus on noise pollution numericals and important concepts related to sound levels. We will understand important formulas, numericals, OSHA exposure standards, CPCB noise pollution standards and practice MCQs and some PYQs. One of the most important concepts in this topic is addition of sound levels. Many students find this topic confusing because decibel calculations are logarithmic, not simple arithmetic. But don't worry, in this lecture we'll understand every concept step by step in a very easy manner. So before starting the formulas, let us understand why noise numericals are important for competitive examinations. Questions related to decibel scale, sound level calculations and noise standards are frequently asked in UGC NET, GATE and environmental sciences examinations. These numericals are based on logarithmic concepts. Once the logic becomes clear, solving questions becomes much easier. These concepts are also important in occupational and environmental noise assessment because they help us understand industrial exposure limits, environmental standards and public health impacts. Most importantly, these are highly scoring topics if practiced properly. That's why noise numericals are important from the perspective of UGC NET JRF Environmental Sciences. So now next is decibel scale basics. So now let's understand the basics of decibel scale. Sound is measured in decibels, commonly represented as dB. The decibel scale is logarithmic in nature, not linear. This means sound levels do not increase in a simple arithmetic manner. 0 decibel represents the threshold of hearing, which is the minimum sound level detectable by the human ear. An increase of 10 decibels means sound intensity becomes 10 times higher. However, from human perception, a 10 dB increase feels approximately twice as loud, but that's not the case. For example, 30 decibel may represent whispering, 60 decibel normal conversation, 90 decibel heavy traffic, and around 120 decibel may occur near a jet engine. Always remember, every 10 dB increase represents a tenfold increase in sound intensity. So now next is logarithmic concept. Now let us understand this logarithmic concept behind decibel calculations. The decibel scale is based on logarithmic to the base 10. The general expression is levels in decibel equals 10 log of quantity divided by the reference quantity. For sound intensity, the formula becomes sound levels equals 10 log I divided by I naught. Here I represents sound intensity and I naught represents reference sound intensity equal to 10 raised to the power minus 12 watt per meter square. So why do we use logarithmics? Because sound intensity covers a very large range. Logarithmic representation helps compress this huge range into manageable numerical values. Remember, 10 dB increase means 10 times increase in intensity, 20 dB means 100 times and 30 dB means 1000 times increase in intensity. Now next is sound pressure level. Now let us study sound pressure level, commonly called SPL. The formula for SPL is SPL equals 20 log P divided by P naught. Here P represents sound pressure and P naught represents reference sound pressure. The standard reference sound pressure is 20 micropascal. Now an important question arises, why do we use 20 in this formula instead of 10? The reason is very simple. Sound intensity is proportional to pressure squared. Therefore, when pressure terms are converted into logarithmic form, the multiplying factor becomes 20 instead of 10. SPL is commonly measured using a sound level meter and is widely used in environmental monitoring, occupational noise assessment, and industrial noise studies. So these were the basic concepts required before solving advanced numericals. Now in the next section, we will start solving important numerical problems step by step. Now next is sound intensity level. The formula for sound intensity level is SIL equals 10 log I divided by I naught. Here I represents sound intensity and I naught represents reference sound intensity. The standard reference sound intensity is 10 raised to the power minus 12 watt per meter square, as we have seen in the previous slide as well. So you may notice that this formula looks similar to the previous logarithmic expression because decibel calculations are fundamentally based on intensity ratios. Here specifically we are applying it to sound intensity level. Sound intensity represents sound power passing through unit area perpendicular to the direction of sound propagation. As sound intensity increases, the sound level in decibels also increases logarithmically. Always remember, sound intensity level is mainly associated with energy flow of sound waves. Now next is the relationship between SPL and SIL. SPL is related to sound pressure while SIL is related to sound intensity. We note that sound intensity is proportional to pressure squared. Because of this relation, SPL formula contains 20 log while SIL formula contains 10 log. This is one of the most important conceptual difference asked in examinations. Students often confuse why 20 log is used in SPL and why 10 log is used in SIL. So always remember, pressure relation gives 20 log and intensity relation gives 10 log. This concept is extremely important for numerical solving. Now next is sound level calculations. In noise pollution numericals, sound levels cannot be added directly because decibel scale is logarithmic, not linear. For example, 70 dB plus 70 dB does not becomes 140 dB. Instead, logarithmic additions methods are used. In environmental engineering and occupational acoustics, these calculations are very important for combined noise assessment, industrial monitoring, traffic noise analysis, and workplace exposure evaluation. In this section, we'll understand different methods used for sound level calculations step by step. So here three formulas are given. First is equivalent continuous sound level, that is LEQ, which is equal to L50 plus L10 minus L50 ka whole square upon 60, where L10 is sound level exceeded for 10% of time, L50 is sound level exceeded for 50% of time, and LEQ is equivalent continuous sound level. Here L10 is the higher percentile level, L50 is the median level, and LEQ represents the average energy of varying sound levels. Second one is sound intensity with distance relation. Here formula is L1 minus L2 is equal to 20 log 10 R2 upon R1. In the pressure formula we have 20 log 10 P upon P naught, but here we have 20 log 10 R2 upon R1, where L1 is sound intensity or sound pressure level at distance R1 and L2 is sound intensity or sound pressure level at distance R2. When distance increases, sound level decreases, and this simply means sound intensity is inversely proportional to distance. Now the third formula is for noise dose, that is exposure calculation. Noise dose is calculated as noise dose percentage is equal to 100 into C1 upon T1 plus C2 upon T2 plus up to Cn upon Tn, where Cn is time spent at each noise level and Tn is permissible time at that noise level. So here important note is decibel scale is logarithmic, not linear. Never add dB values directly. Always use the table for accurate addition. So now we are at sound level calculations, that is decibel scale sound level calculations, specifically addition of sound levels. As we know, it is not done by simple arithmetic, so I have given you here the table. You can also call it a shortcut method which can be used in examinations to save your time. So the table has two columns. First column is difference between two decibel levels to be added, that is from 0 to 12, and the column 2 says amount to be added to the larger level to obtain decibel sum. So example, we can see here we have two values 50 dB plus 55 dB. Difference between them is 5 dB. So for 5 dB in the table we have the value 1.2. So we will need to add 1.2 to the larger value, that is 55 dB. So the resultant decibel level is 56.2 dB. So exam shortcut here is find the difference between two levels, look up the value in the table, add that value to the higher level, that gives the total sound level. And here we have the solved MCQ. Two machine produces sound levels of 70 dB and 73 dB respectively. The combined sound level will be approximately, we are given four options. So we need to see the table. The difference between two levels is 3 dB. From the table, 3 dB difference amount to be added is 1.8 dB. So we need to add 1.8 dB to 73 dB and the resultant becomes 74.8 dB, that is approximately 75 dB. So this shortcut method saves a lot of time in the examinations. Now next is the conventional method. So here we are given an MCQ for numerical practice, and an MCQ asks two sources of noise adjacent to each other in a room have sound pressure levels of 30 dB and 40 dB. The combined sound pressure level we need to calculate in the room. So we are given L1 30 dB and L2 40 dB, where L1 is lower level and L2 is higher level. Formula here will be L total is equal to 10 log 10 raised to power L1 upon 10 plus 10 raised to power L2 upon 10. This is the conventional formula, conventional method. So substituting the values, L total becomes 10 log 10 raised to power 30 upon 10 plus 10 raised to power 40 upon 10. So it becomes 10 log 10 raised to power 3 plus 10 raised to power 4. On calculation it becomes 40.41 dB. Therefore the combined sound level is 40.41 dB. And if we go through the table method, the shortcut method, higher level is 40 dB, lower level is 30 dB. The difference between them is 10 dB. So from the standard addition table, for difference of 10 dB, we have 0.4 dB to be added to the higher level. So the combined level becomes L2, that is the higher value, higher level, plus 0.4 from the table, that is 40 plus 0.4 is 40.4 dB. So it is approximately equal to 40.41 dB. So for exact answer use conventional formula, and for quick exam approach use table method. So the next is sound level calculations. We are given an MCQ which we have solved earlier from the table method. Now here we are solving the same MCQ using the conventional method. So the solution becomes the two machines produces sound levels of 70 dB and 73 dB respectively. The combined sound level will be approximately, we are given four options, 143, 76, 73 and 80 dB. So from conventional method we have formula L total is equal to 10 log 10 raised to power L1 upon 10 plus 10 raised to power L2 upon 10. On putting the values and substituting the values, we will get L total as 74.76, that is approximately 75 dB. As you can see the calculation, it is very simple calculation. So the takeaway here is total sound level is approximately 75 dB. Comparison with table method, difference is 3 dB. From table add 1.8. So we need to add 1.8 to 73 dB, which will give us 74.8 dB, that is approximately equal to 75 dB. So both methods are giving the same result. So option B 76 dB approximately, nearest option to 75 dB is the answer. We need to note here that conventional exact method is accurate but time consuming. Shortcut table method is preferred in exams for quick calculations. So next slide is subtraction of sound levels. Now let us understand subtraction of sound levels, which is very important in environmental noise monitoring and industrial acoustics. Many times we measure total noise that includes both background noise and the actual source noise. To find the contribution of a specific source, we cannot simply subtract decimal values directly because the decimal scale is logarithmic in nature. For accurate calculation, we first convert decibel values into linear intensity form, then subtract the background component and finally convert the result back into decibels. Here the formula shown is used to calculate the actual source sound level from the total measured noise and the background noise. So let us take the practical example shown on the slide. Suppose the total measured noise is 75 decibels and the background noise is 70 decibels. After applying the logarithmic subtraction formula, the isolated source sound level becomes approximately 73.3 decibels. The slide also shows a quick rule of thumb. used in field situations. If the difference between total noise and the background noise is very small, especially less than 3 decibels, then accurate subtraction becomes difficult because the background noise contribution is too high. So remember here, decibel values should never be subtracted directly by normal arithmetic methods. Always use logarithmic subtractions for accurate environmental noise analysis. So next is, now let us solve an important numerical based on sound power and sound intensity level. So read the question carefully. A relatively calm room has a background sound power level SPL of 30 decibels. A television and a radio with SPL of 80 dB and 70 dB respectively started operating simultaneously in the room. Given the reference sound power is 10 raised to power minus 12 watts, what will be the resulting SPL in the room, assuming all the sources operate independently? So here the formula given is, firstly we need the formula to convert SPL in dB to sound power in P. So L is equal to 10 raised to power P upon P naught, where P naught is 10 raised to power minus 12 watts given. Follow these steps to find P. Now firstly we need to rearrange the formula to isolate P upon P naught. So that is L upon 10 is equal to log P upon P naught. Now we need to apply here anti-log, that is 10 raised to power to both sides. Now anti-log, if log x is y, then x is equal to 10 raised to power y in case of anti-log. So 10 raised to power L upon 10 becomes P upon P naught. Multiply both sides by P naught to get P. So P is 10 raised to power L upon 10 into P naught, that is 10 raised to power L upon 10 into 10 raised to power minus 12. So now we need to calculate power for each source. So for background sound, that is 30 dB, we have P background is equal to 10 raised to power 30 upon 10 into 10 raised to power minus 12. That is, on calculation we'll get 10 raised to power minus 9 watts. And for television set, similarly on calculation we get 10 raised to power minus 4 watts. And for radio, which is of 70 dB, we get 10 raised to power minus 5 watts. So in the step 4, we need to add all the powers since sources are independent. So P total becomes P background plus P TV plus P radio. That is 10 raised to power minus 9 plus 10 raised to power minus 4 plus 10 raised to power minus 5. So it becomes 1.11 into 10 raised to power minus 4 watts on calculation. I am not showing here the calculation part because otherwise the video will become very long. So I am expecting that you guys can solve these basic calculations by yourself. So now we need to convert total power back to SPL in the step 5. So L total is 10 log P total upon P naught, that is 10 log numerator 1.11 into 10 raised to power minus 4 upon 10 raised to power minus 12 in denominator. So on solving we'll get 10 into log 1.1 plus log 10 raised to power 8. So using here simple basic log rules, that is log AB is log A plus log B, and log 10 raised to power n is n. So on solving we'll get here 80.414 dB, that is rounded off to 2 decimal places, that is 80.41 dB. So now let us understand frequency and the range of human hearing. Sound is a mechanical wave and one of its most important properties is frequency. Frequency simply means the number of vibrations or oscillations produced per second. The unit of frequency, as we know, is hertz, written as Hz. 1 hertz means 1 vibration per second. Now humans cannot hear all frequencies. Our ears can detect only a limited range of sound frequencies. Based on frequency, sounds are divided into 3 categories. First is infrasound. Infrasound includes frequencies below 20 Hz. These frequencies are lower than the normal hearing range of humans. Examples include elephant cells and certain natural phenomena like earthquake and volcanic vibrations. Second is audible sound. This is the normal hearing range of humans, extending from 20 Hz to 20,000 Hz, that is 20 kHz. Most daily life sounds, including human speech, music and traffic noise, falls within this range. Human speech generally lies between about 250 Hz to 4 kHz. Third is ultrasound. Ultrasound includes frequencies above 20,000 Hz. These sounds cannot be heard by humans but are used in many scientific and medical applications. For example, dog whistles and bat echolocation use ultrasonic frequencies. Ultrasound is also widely used in medical imaging, sonar systems and industrial testing. So remember, below 20 Hz is infrasound, 20 Hz to 20 kHz is audible sound, and above 20 kHz is ultrasound. This classification is very important for UGC NET GATE and other environmental science examinations. So now we are at slide number 15. Now let us understand frequency weighting networks, which are very important in environmental noise measurement. The human ear does not respond equally to all frequencies. Our ears are most sensitive to frequencies between 1 kHz and 5 kHz. Very low frequency and very high frequency sounds are perceived as less loud even if their actual energy is high. To account for this behavior of the human ear, sound level meters use different frequency weighting networks. These weighting systems modify the measured sound level to better represent human hearing perception. The most commonly used weighting curves are A weighting, C weighting and Z weighting. First is A weighting, written as dBA. A weighting closely represents the sensitivity of the human ear at normal listening levels. It significantly reduces low frequency and very high frequency sounds. Because of this, A weighting is most commonly used in environmental noise monitoring and legal noise standards. For example, traffic noise is usually reported in dBA. Second is C weighting, written as dBC. C weighting has a flatter response compared to A weighting and gives less attenuation at low frequencies. It is mainly used for high sound level situations such as industrial machinery, explosions and heavy equipment noise. Third is Z weighting, written as dBZ. Z weighting is a flat or linear response. In this case, all frequencies are measured equally without any adjustment. It is mainly used for scientific analysis and acoustical research. Now look at the conceptual frequency response graph shown below. The blue curve represents A weighting, the green curve represents C weighting, and the red straight line represents Z weighting. Always remember, when comparing sound levels, check whether the measurement is given in dBA, dBC or dBZ, because the weighting network affects the final reading. Among all weighting networks, A weighting is the most important and most commonly asked in examinations. Now next is, let us study sound measurement instruments used in environmental noise analysis. These instruments help us measure, analyze and record sound levels accurately. The most important instrument is the sound level meter, commonly called SLM. A sound level meter measures sound pressure level in decibels or dB. It mainly consists of a microphone, preamplifier, processor and display unit. The microphone receives sound waves, the processor converts them into electrical signals, and the display shows the sound level reading. Modern sound level meters can measure A weighted, C weighted and Z weighted sound levels. These instruments are widely used in environmental noise monitoring, industrial hygiene studies and regulatory compliance. Now let us discuss some important features of a good sound level meter. A good sound level meter should have a wide frequency range, usually from 20 Hz to 20 kHz. It should support multiple weighting networks such as A, C and Z weighting. It should also provide fast and slow response modes depending on the type of sound being measured. Other important features include high accuracy, calibration stability, data logging and USB or computer connectivity. For outer measurements, weather protection and a windscreen on the microphone are also important. Now let us look at some other important sound measurement instruments. First is the sound calibrator. A sound calibrator generates a known sound level such as 94 decibels at 1 kHz to check the accuracy of sound level meters. Second is the octave band analyzer. This instrument measures sound levels in different frequency bands and helps identify dominant frequencies in noise. Third is the noise dosimeter. A noise dosimeter measures personal noise exposure over a period of time and is commonly used in occupational health studies. Fourth is the integrating sound level meter. This instrument measures equivalent continuous noise level, also called LEQ, over a specific duration. Finally, always remember, regular calibration of instruments is essential for accurate and reliable noise measurements. Now next is noise exposure and effects on human health. Noise pollution is not only an environmental issue but also a major public health concern. Long-term exposure to high sound levels can affect both physical and psychological health. The effects of noise depends mainly on sound intensity, frequency, duration of exposure and individual sensitivity. Now let us discuss some major health effects of noise pollution. First is hearing loss. Continuous exposure to loud sound can damage the hair cells present inside the inner ear. This may lead to temporary hearing loss or permanent hearing impairment. Very high sound levels over long durations can even cause noise-induced hearing loss, commonly called NIHL. Second is sleep disturbance. Noise during night time affects sleep quality and interrupts normal sleep cycles. Poor sleep may lead to fatigue, reduced concentration, and mental stress. Third is cardiovascular effects. Research studies show that long-term exposure to environmental noise may increase blood pressure, heart rate, and risk of cardiovascular diseases. Traffic noise and industrial noise are major contributors in this. Fourth is psychological stress. Excessive noise can cause irritation, anxiety, frustration, and reduced mental performance. Students and workers exposed to high noise levels may experience reduced productivity and concentration problems. Fifth is communication interference. High background noise affects speech communication and makes conversation difficult, especially in classrooms, offices, and hospitals, and even on YouTube videos. Now look at the exposure guideline values shown in this slide. According to WHO recommendations, prolonged exposure above safe limits may create serious health risks. Similarly, NIOSH defined occupational exposure limits for industrial workers. NIOSH stands for National Institute for Occupational Safety and Health. It is also a US organization that gives recommended occupational safety and noise exposure limits. For example, exposure to 85 dBA for 8 hours is considered an important occupational safety threshold. As sound level increases, the safe exposure duration decreases rapidly. Therefore, noise control and hearing protection become extremely important in workplaces and urban environments. Always remember, noise pollution affects not only hearing but overall human health and quality of life. Now let's come to the next slide. Here let us solve an important conceptual MCQ related to sound power and sound intensity. These type of questions are frequently asked in UGC NET and other competitive examinations. The question is based on relationship between sound power, sound intensity and decibel scale. And the question asks, consider the following statements. 1. Sound pressure changes with distance from the source. Second, sound power is a property of the source. Third, sound intensity is sound power per unit volume. We need to choose the correct option from the following. So now let's see. To solve such questions correctly, students must clearly understand the logarithmic nature of sound measurements. Always remember, sound power represents the total acoustic energy emitted by a source per unit time. However, sound intensity represents sound power passing through unit area perpendicular to the direction of sound propagation. Mathematically, sound intensity is equal to sound power divided by area. Now, another important point here is the decibel scale is logarithmic, not linear. Because of this, a small increase in decibel value actually represents a large increase in sound energy, as we have discussed multiple times previously in this video. For example, an increase of 10 decibels means sound intensity becomes 10 times greater, not double. Similarly, 20 decibel increase means 100 times increase, and 30 decibel increase means 1000 times increase in intensity. This is one of the most important concepts in environmental acoustics. Now analyze the options carefully. Many students make mistakes because they confuse sound intensity, sound pressure and perceived loudness. So always focus on the physical meaning of the quantity, the unit involved and the logarithmic relation. Questions from this area are usually conceptual rather than calculation based. Therefore, understanding the logic behind the formula is more important than memorizing equations blindly. So here, first option is true because sound pressure does indeed decrease with distance from the source because sound spreads out as it travels, causing the intensity and pressure to diminish. Second option is also true because sound power is an inherent property of the source representing the total energy output per unit of time irrespective of the environment. But the third option is false. Third option is sound intensity is sound power per unit volume. But sound intensity refers to sound power per unit area, not per unit volume. It is typically measured in watts per square meter, that is W per meter square, not in the terms of volume. Therefore, only option 1 and 2 are correct, making option B the right choice. So, option B, only 1 and 2 are correct, is the correct answer. Now, next slide is noise pollution sources, standards and control. Noise pollution originates from multiple natural and human-made sources. However, in modern urban environments, most noise pollution is anthropogenic, meaning human-generated. One of the major sources is transportation noise. This includes road traffic, railways, and aircraft noise. Among these, road traffic noise is one of the most dominant sources in urban areas. Second is industrial noise. Factories, heavy machinery, generators, compressors, and manufacturing units produce high intensity sound levels, especially in industrial zones. Third is construction noise. Construction activities such as drilling, demolition, hammering and concrete mixing generates very high temporary noise levels. Fourth is community noise. This includes loudspeakers, social events, markets, household appliances and public gatherings. Now let us discuss noise standard. In India, ambient noise standards are prescribed by CPCB, which stands for Central Pollution Control Board. Different noise limits are specified for industrial area, commercial area, residential area and silent zones. For example, residential areas generally have lower permissible noise limits compared to commercial and industrial areas. Silent zones such as hospitals and educational institutions have the strictest noise standards. Now look at the table shown in the slide. These standards are generally expressed in terms of dBA LEQ. Here dBA represents a weighted decibel scale and LEQ represents equivalent continuous sound level over a specified duration. Now let us briefly discuss control measures. Noise pollution can be controlled at three levels, that is source control, path control and receiver protection. Source control includes proper maintenance of machinery, silencers and low noise equipment. Path control includes sound barriers, green belts and acoustic insulation. Receiver protection includes earplugs, earmuffs, and personal protective equipments. Always remember, prevention and control of noise pollution are essential not only for environmental protection but also for public health and occupational safety. Now next is noise pollution control and mitigation strategies in detail. As we know, effective noise control is essential for protecting human health, improving environmental quality and maintaining occupational safety, as we discussed in the previous slide. Noise mitigation strategies are generally classified into three major categories as we discussed in the previous slide, that is at source, along the transmission path and at the receiver end. First is control at source. Let's discuss the mitigation strategies in detail here. This is considered the most effective method because it reduces noise before it spreads into the environment. Source control methods include regular maintenance of machinery, lubrication of moving parts, use of silencers and mufflers, vibration isolation and adoption of low noise equipment. In industries, proper machine design and acoustic enclosures are also widely used. Second is control along the transmission path. In this method, barriers are created between the source and the receiver. Example includes sound barriers, acoustic walls, green belts, double glazed windows and sound absorbing materials. Vegetation and green belts can also help reduce noise to some extent in urban areas. The recent example is Delhi-Dehradun Expressway. On the wildlife corridor section of Delhi-Dehradun Expressway, which starts from Ganeshpur and till up to the Datkali temple, the 12-kilometer wildlife corridor area has the sound barrier installed by the National Highway Authority of India. So that's the best example in transmission path. Third is receiver protection. When source control and path control are insufficient, personal protection becomes important. This includes earplugs, earmuffs, acoustic helmets, and limiting exposure duration. Workers exposed to high industrial noise must use proper hearing protection devices. Now let us discuss administrative and planning measures. Urban planning plays a very important role in noise management. For example, industrial zones should be separated from residential areas. Similarly, silent zones should be maintained near hospitals, schools and courts. Traffic management, speed regulation, vehicle maintenance and restrictions on loudspeakers are also important mitigation measures. Public awareness is equally important because community participation helps in long-term noise reduction. Always remember, the best strategy for noise pollution control is prevention at the source itself. Once noise spreads into the environment, mitigation becomes more difficult and expensive. So next is the case study of the Indian cities from the perspective of noise pollution. As we know, rapid urbanization, industrialization, and increasing traffic density have significantly increased environmental noise levels in many metropolitan regions of India, especially the Delhi NCR region. Major sites such as Delhi, Mumbai, Kolkata, Bengaluru, and Chennai frequently experience noise levels above permissible CPCB standards. One of the biggest contributors is road and highways traffic noise. Continuous honking, engine noise, congestion, and poor traffic management create high sound levels, especially during peak hours. Construction activities in commercial zones further increase urban noise burden. Now observe the data and graphical representation shown in the slide. In many urban locations, the measured sound levels exceed CPCB permissible limits, particularly in commercial and traffic-dominated areas. Even residential zones often experiences sound levels higher than recommended standards during daytime and nighttime. This situation becomes more serious near highways, railway stations, airports, industrial clusters, and dense populated marketplaces. Now let us discuss the impacts. Continuous exposure to urban noise may lead to stress, sleep disturbance, reduced concentration, hypertension, and long-term hearing related problems. Children, elderly people, and hospital patients are especially vulnerable. Now, let us understand the importance of monitoring and management. Regular environmental noise monitoring is necessary to identify high risk zones and implement corrective measures. Some important control strategies adopted in cities include traffic regulation, silent zones near hospitals and schools, green belt development, vehicular maintenance, and restrictions on pressure horns and loudspeakers. Public awareness and strict implementation of environmental regulations are equally important for effective noise management. This case study clearly shows that noise pollution is not only a scientific issue but also a major environmental and public health challenge in modern urban society, especially in regions like Delhi NCR and Chandigarh Tri-City and other metropolitan areas. Now let us summarize the important concepts discussed in this lecture. In this complete session, we studied the fundamentals of noise pollution along with the important numerical and conceptual topics relevant for competitive exams. Firstly, we understood the decibel scale and its logarithmic nature. We learned that sound levels cannot be added or subtracted using simple arithmetic methods because decibel is a logarithmic unit. Then we discussed important formulas related to sound pressure level, sound intensity level, and logarithmic sound calculations. We also solved important numericals based on addition of sound levels, subtraction of sound levels, and combined sound pressure calculations. After that, we studied frequency ranges, human hearing limits, and frequency weighting networks such as A, C, and Z weighting. We also discussed sound measurement instruments including sound level meter, noise dosimeter, octave band analyzer, and sound calibrator. Then we explored the health impacts of noise pollution such as hearing loss, sleep disturbance, psychological stress, and cardiovascular effects. We also studied important standards and guidelines including CPCB standards, WHO recommendations, and in the next slide we'll study OSHA occupational exposure limits. Finally, we discussed practical control and mitigation strategies along with a case study related to noise pollution in Indian cities. Always remember, for competitive examinations, conceptual clarity is more important than memorization. If your logarithmic concept and decibel calculations become clear, most noise pollution numericals becomes easy to solve. So revise the formulas regularly, practice numericals consistently, and focus on understanding the logic behind each concept. Although we have completed almost everything before this slide up to the key summary takeaways, but this slide was important, the information in this slide was important, so I added this slide later on. So this slide discusses about OSHA standards, that is OSHA standards, WHO guidelines, and international standards. These standards are extremely important from both examination and practical environmental management perspective. First, let us understand OSHA standards. OSHA stands for Occupational Safety and Health Administration. It is a US government agency responsible for workplace safety and occupational health regulations. According to these standards, workers can be exposed to 90 dBA noise for a maximum duration of 8 hours per day. Now notice an important trend. As sound level increases, the permissible exposure duration decreases rapidly. For example, at 95, safe exposure duration reduces to 4 hours, and at 100 dBA it becomes only 2 hours. This happens because high intensity sound can damage hearing much faster. Now let us look at the WHO guidelines. As we know, WHO stands for World Health Organization. WHO provides environmental noise recommendations to protect public health and quality of life. For residential areas, WHO recommends that daytime outdoor noise should generally remain around 55 dB LAEQ or lower. For nighttime conditions, the recommended level is even lower because excessive nighttime noise affects sleep quality and mental health. Now let us understand NIOSH recommendation. NIOSH stands for National Institute for Occupational Safety and Health. NIOSH recommends a stricter occupational exposure limit compared to OSHA. According to NIOSH, 85 dBA for 8 hours is considered the recommended occupational exposure limit. This recommendation is more protective for long-term hearing safety. Now look at the EU and ISO standards shown in the slide. These international standards help maintain consistency in occupational noise management, industrial monitoring, and environmental assessment. One very important thing to remember is most environmental noise standards are expressed in terms of dBA, LA, EQ. As we discussed earlier as well multiple times here, dBA indicates A-weighted sound measurements and LAEQ represents equivalent continuous sound level over a specified duration. These standards are widely used in industrial safety, urban noise monitoring, occupational exposure assessment, and environmental impact studies. For competitive examination, students should focus mainly on OSHA exposure limits, WHO environmental recommendations, NIOSH limits, and the meaning of dBA and LAEQ. These are frequently asked conceptual areas in the UGC NET and environmental science examinations. One small note here before ending. NIOSH here stands for National Institute for Occupational Safety and Health. As I told you, it is also a US organization that gives recommended occupational safety and noise exposure limits. So thank you everyone for watching this complete lecture on noise pollution. I hope this session helped you understand decibel concepts, logarithmic calculations, important numericals, noise standards, and environmental applications in a simple and exam oriented manner. If you found this lecture useful, then do support the channel by liking the video, sharing it with your friends, and subscribing to Science Pathshala for more environmental science lectures, numericals, and exam preparation content. Keep learning, keep growing, and keep moving one step closer towards your goals. Thank you once again. See you in the next lecture. Thank you so much.